So let me get this right. You can actually manufacture 2D pixel arrays at 1.3 micrometers, totally eye-safe, emitting 8 watts QCW?
Absolutely right. Please come and see for yourself. You can visit us anytime.
Are you sure? I'm coming right now.
Absolutely.
I love pixels. For the last 10 years, I've been traveling the world, visiting great companies to gain industrial insights firsthand. Now, as I prepare for my new job starting March 1st, I'm flying to see VERTILAS. The 3D sensing industry has always been concerned about eye safety. Pixels operating between 810 and 940 nanometers are often used in 3D sensing. The human eye cannot detect these near-infrared wavelengths, yet these lasers can potentially damage the eye as a result of long-term exposure. At the same time, there is a need for low cost, high power, and high efficiency. That's why I am in the car, late at night, on my way to the outskirts of Munich.
Yes! I'm engaging outside Munich to see those 1.3 micrometer emitting pixels with 8 watts of power from VERTILAS. I can't believe we made it. Let's see it!
Welcome, Jose. Thank you for visiting us today. It's really great having you here and discuss about our technology.
When did you realize that these wavelengths that you are targeting could actually solve problems for this 3D sensing?
We've been talking to people in this market, or they have approaching us, and we noticed that eye safety is very important because this 3D sensing requires lasers with relatively high or very high output power, starting at maybe tens of milliwatts and then going all the way up to tens of watts of power in QCW mode.
As you told me on the phone, one of the highlights of the tour today will be to see a 2D pixel array in a sensor machine. But I'm going to use already our camera here for the audience to already see a 1000 pixel array, which is the small chip in the middle of these two large contacts on the top of a copper surmount. The future is very bright, very illuminated for VERTILAS. That was a really fantastic idea. I am so happy to be here. What are you going to show me? Let's go already. Let's
go. We'll show you how we produce the lasers.
Christian took me to the labs. As a fan of testing and qualification, I wanted to see how these pixels were being tested, especially with regards to lifetime. I see that there are 3 ovens here, one for 50, 70 and 90 degrees, and there is another little oven over there.
Actually running already for 50,000 hours.
50,000 hours. How much is that in years?
This campaign is running for about 7-8 years now.
8 years?
Yeah.
8 years of having the pixels in there, being tested periodically for life tests.
Yeah. Reliability and lifetime for our VCSEL is of course the most important when shipping products into the field. We're looking at a 10 gigabit eye of our 1.3 micron laser. It's a 1310 nanometer laser, which can be used for data communications for reach up to 10 kilometers or even more, but the standard is for 10 kilometers. Okay, Jose, now you've seen our backend facility with assembly and test, and the next stop will be the clean room, wafer production. So let's go.
Let's go. The Walter Schottky Institute, very well known for gallium antimonide research, and of course this is where you do your indium phosphide magic for the VERTILAS VCSELs. It was totally worth it to come all the way from Amsterdam to Garching to see the magic made in place. 8 watts of power coming out of 2D VCSEL arrays. 800 VCSELs in these 2D VCSEL arrays being tested and validated with Telcordia standard approval. 8 years into the oven to make sure they had the right lifetime, making a difference in the future automotive, in the future consumer electronics. This is the one to watch. Thank you very much, Christian, for having me here. I'm going to the airport.
I love it when people innovate by thinking outside the box. For 20 years, VERTILAS has been making a difference in 1.3 and 1.5 micrometer wavelengths in telecom and gas sensing applications. Now they managed to increase the output power to open the biggest pixel market, 3D sensing.